Let's start with a simple experiment. I have a file with 64 kilobytes of data. Watch what happens when I compress it using the zip format. Wait, what? The compressed file is actually larger than the original? Well, this video is going to explain something that seems impossible. Why compression shouldn't work mathematically, but somehow it does work for almost everything that we use every day. By the end, you will understand why your favorite videos, images, and files can shrink to a fraction of their size, and why sometimes, like we just saw, they can't. Here is a text message on screen. Now normally, when computers store text, they use ASCII format. If you are screaming UTF-8, I hear you, but let's assume ASCII for simplicity. In ASCII format, every character takes exactly 8 bits. That means our message uses 23 characters times 8 bits each, which is equal to 184 bits total. But wait, look closely at what characters we are actually using. That's only 7 unique symbols. Do we really need the full power of ASCII, which can represent 256 different characters? That seems wasteful. Here's an idea. What if we create our own mini alphabet with just 7 symbols? We only need 3 bits per character, because 2 raised to the power 3 equals 8, which gives us the room for all of our symbols. And with this, we saved 115 bits. That's over 60% reduction. Not bad for our first attempt. But here's where the approach starts to crack. As we use more and more unique symbols, we need more bits to represent each one. With 7 symbols, we need 3 bits. With 15, we would need 4 bits. And with 129, we're back to needing 8 bits. And we have gained nothing. Our clever compression scheme only works when we're using a tiny fraction of possible characters. We need something better. And to find it, we need to look back in time. The year is 1837. Samuel Morse is working on a revolutionary idea: transmitting information across long distances using signals. He develops what we now know as Morse code, a system of dots and dashes. But here is the brilliant part. Morse didn't give every letter the same length code. He noticed that in English language, some letters appear far more frequently than others. The letter E appears constantly, so he gave it the shortest code, just a single dot. The letter T also appears often, a single dash. Meanwhile, rare letters like Q got longer, more complex codes. This is the key insight: variable length encoding. Frequent symbols get short codes, rare symbols get long codes. On average, you save space because you're optimizing for what actually appears in the real data. Our fixed length scheme from earlier treated every character equally. Every symbol got exactly 3 bits. But that's not how information actually works in the real world. There are patterns. If we can exploit these, we can compress data. Let's apply this idea to our message by counting how often each character appears. Then, we assign shorter codes to the frequent characters and so forth. Then, we can simply substitute the bits. Once we have compressed string ready, we should also test if the decompression works as expected. Next, we read bits one by one. 0, that's P. 1, that's E. 1 again, and that's E again. Hold on, our original message started from pen. The bits 1, 0 could mean E, then P, or they could mean N. It's ambiguous. The problem is that multiple symbols share the same bit prefix. So, while reading bits, we can't tell where one symbol ends and another begins. A compression algorithm that can't reliably decompress the data is useless. So, how do we fix this? Once again, we turn to history. In 1952, a graduate student named David Huffman was taking information theory course at MIT. His professor gave the class a choice: take final exam or write a paper on finding the most efficient binary code. Huffman chose paper and discovered something remarkable. He created an algorithm for prefix-free code, where no code is a prefix of any other code. This completely solves our ambiguity problem. And better yet, it's mathematically optimal for compressing individual symbols. Here is how it works. We start with our message with frequencies of each character. Then, we create nodes for each symbol with their frequencies. Then, we pick two of the least frequent nodes and merge them. We keep doing this until we have a unified tree left. After the process, we will have a root node with total frequency of 23, which matches our message length of 23 characters. Now, the interesting part is every symbol is a leaf of this tree. And by fundamental properties of tree, there is exactly one path from the root to each leaf. Let's label the left branch with 0 and the right branch with 1. Want to find out the code for I? Start with the root node and traverse to I. Keep noting the bits while traversing. After traversal, we got the code for I, that is 0011. Following the same procedure for all the nodes we get, notice what happened. P appears 7 times and gets a short 2-bit code, while I appears once and gets a long 4-bit code. The algorithm automatically gave shorter codes to frequent symbols in a mathematically optimal way. And here's the crucial part. This is a prefix-free code. Look at the tree. P is 01, but no other symbol starts with 01. E is 10, and no other symbol starts with 10. Every code is unique, and no code is a prefix of another. Let's compress our message now. P is 01, E is 10, N is 000, and following the same procedure for all symbols, we get the compressed bits. Now, to decompress the bits, we start at the root, read bits, and traverse through the tree. For 0, we move left, 1, we move right, and we are at the leaf node. So, bit 01 stand for P. Similarly, we read 1, traverse right, we read 0, traverse left, and we reach the leaf again. This time it's E. And following the same procedure, we were able to reconstruct our original message. Huffman coding is elegant and optimal, but only for what's called first-order entropy. It treats each character as independent, ignoring the context around it. But real data has deeper patterns. In English, after the letter Q, you almost always see U. After TH, you often see E. These are the patterns between characters and not just individual character frequencies. In 1977, Abraham Lempel and Jacob Ziv published a revolutionary paper introducing what we now call as LZ compression. Instead of encoding individual characters, LZ algorithms look for repeated sequences and replace them with back reference to earlier occurrences. Here's a simple example. Imagine we are compressing this text again. We first encounter some set of bits which we did not see before, so we output them as is. Again, the bit stream that we encountered wasn't seen before, so we continue processing. Interestingly, now we see a string which was seen before, so instead of streaming bits, we would say go back 6 characters and copy 5 characters. The back reference take far fewer bits than encoding 5 letters separately. Now we process further. We again have a string which we saw before, so again we output a back reference. And by that we completed the compression. Pretty neat, right? LZ77, one of the original variants, uses a sliding window to search for matches. As you encode, you look backward in the data you've already processed. Found a match? Output a back reference. No match? Output the literal character and keep going. This is a game changer because it exploits redundancy at a much deeper level. And it is the foundation for almost every compression that we use today. Great, let's take a pause and think about the video on screen. It's a 4K video with 3 channels in 30 FPS. Doing some math reveals even 60 seconds of this video without audio would be very inefficient. But thanks to formats like H265, you're able to stream this. Not just the videos, even the YouTube page and the JS bundles were 17 megabytes, which were compressed into 3.5 megabytes, saving a ton of YouTube bandwidth. YouTube uses Brotli compression, but all the formats like Brotli, gzip, zip, they all use LZ compression and Huffman encoding. So what we just saw is extensively used in the real world. There are a lot of other ways of compressing things: differential compression, run length encoding, lossless compression, and even ML based compressions. But all of these, every single one, rest on the fundamental ideas we've explored: exploiting patterns, variable length encoding, and redundancy elimination. Speaking of algorithms, if you enjoyed diving deep into how compression works, you'll love today's sponsor, Brilliant. Brilliant will transform you into a better problem solver. Their platform is designed to be highly effective, with a perfect mix of interactive problems, motivating challenges, and encouragement to keep you moving forward. What I love about Brilliant is that it personalizes learning for you. It starts you at the right level based on your background. The platform is crafted by award-winning team of teachers, researchers, and professionals. Whether you want to master algorithms, dive deeper into computer science, or explore mathematical thinking, Brilliant has courses that makes complex topics intuitive and engaging. To learn for free on Brilliant for a full 30 days, go to brilliant.org/premature optimization or click the link in the description. Brilliant has also given our viewers 20% off on annual premium subscription, which gives you unlimited daily access to everything on Brilliant. So you get 30 days free plus 20% off if you decide to upgrade. So let's return to where we started. Why does compression work when mathematically it shouldn't? To answer this, let's assume that there exists a function that takes a file of x bits and compresses it into a file of at most x minus 1 bits. Now imagine if I compress the compressed file again, which was x minus 1 bit, would it turn it into x minus 2 bits in size? And what if I keep on doing this x times? Then would my file size be 0? Why even stop there? Let's compress it x times more. And did we create x bits of extra storage just by compressing the file? Obviously, it's impossible. So, what went wrong? The answer is profound and was proven mathematically by Claude Shannon in 1948. He introduced the concept of entropy, the minimum number of bits needed to represent information without loss. Entropy depends on patterns in your data. Highly structured data, like repeating characters, has low entropy. You can compress it massively because there's a simple pattern. Completely random data, like digits of pi or truly random noise, has maximum entropy. There are no patterns to exploit. Every bit is unpredictable. Therefore, you cannot compress it. It isn't a failure of algorithms, it's a fundamental law of information theory. Shannon proved that you cannot compress a data below its entropy without losing information. If data has n bits of entropy, you need at least n bits to store it perfectly. Random data has maximum entropy. Every bit matters. There's nothing redundant to remove, no patterns to exploit. Compression algorithms can only rearrange the bits or add metadata, which makes the file larger. This is why 64 KB file from beginning got bigger when we compressed it. It consisted of random bits, so the compression algorithm had no patterns to exploit. And it just added its own metadata and overhead. But here's the beautiful thing. The files that we use every day are not random. They're filled with patterns. Text has patterns. In English, characters have different frequencies, words repeat, grammar and syntax create predictable structures. Images have patterns. Photo of sky has vast regions of similar blue pixels. Photos of buildings have straight lines and repeated textures. Even complex images have correlations. Video have even more patterns. Most of the time, consecutive frames are nearly identical. Only small parts of the scene change. That's why video compression focuses on motion prediction and differential encoding. Even random-looking data often has hidden structures. All of these patterns are exploitable, and that's why compression works. It's not magic, it's maths. It's recognizing that information is rarely random, and redundancy is everywhere, if you know how to find it and eliminate it. Thank you so much for watching, and I hope that you learned something new from this video.